Hello, welcome back. Today, put it to a vote. We're going to be doing more with servos and Glasgow today. So I've got the same servo fixture I had from last time. We were playing with this servo, so watch out. Hopefully it'll move soon. And the idea today is to just polish off the applet a bit. I'd quite like to have the ability to position the servo remotely, and I'd also quite like to do sort of things like speed control and ramping, that kind of thing, so that it can start slowly, move quickly, and then slow down again at the end. So let's bring Glasgow in shot as well. It's going to get possibly a little bit busy under the camera today. There you go. What we're going to have then is common ground for everybody to speak on, and we're going to connect up to channel A or pin A0, which will give us the servo position control. And then I've got these orange and brown wires just here are going to go off to the power supply. We found that the Glasgow isn't really able to power these servos, so we're just going to use a proper bench supply for that instead. I've brought my wires over already, so I'm nicely prepared this week. I grab it end on. There's that one. And this one. Okay. Hopefully that is all in shot and everyone can see it okay. This board here, you can just ignore that. Actually, maybe I'll just remove it completely. It's the board we're using to control this fixture. There we go. So it's not related to this evening. Okay. This breadboard that's just on the corner here is just to connect up the power so that we can plug in the power supply and also get common ground as well. Okay, so come back to computer. We are going to continue with our servo applet. Let's just grab that. It's in so software, Glasgow applets. Where did I put it? I think it's probably in control, servo, no. Oh, if I put it on a branch, I probably cleaned up after last time. There we go. And that went into applet control servo ppm. So that should be here. Out into control servo ppm. There we go. Oh, still going. Don't know about that. Where would you be? Mind. Okay. Get rid of you. Sorry about that. Still running from the last stream. Okay. Cool. There we go. Right, so previously we just had it going and counting. I'm not sure if anyone wants an explainer, but basically servos take a control input which varies from a 1 millisecond to a 2 millisecond pulse width, and then on a 50-ish hertz frequency. So if you give it a 1 millisecond pulse, it will be all the way in one direction. If you give it a 2 millisecond pulse, it'll be all the way in the other direction. And then 1.5 millisecond pulse will be dead center kind of thing. So what we're doing here is we are starting up, and then we're just going to count up, sweep it one way, and then we're going to count down, sweep it back the other way. And it's just going to do that forever and ever. I'll get my power supply running again. 5 volts, 4 amps, I think should be fine, and we should be good to go. Like that, there we go. And then if we get Glasgow running, servo ppm, do you reckon it was? No. Oh, control servo ppm output, of course. And we do a 5 volt output. Let me just see which one this is. The 3714. 3714. Yeah, I've got two Glasgows connected to this computer, which is why it was asking me which one to use. There we go. Brilliant. So as we can see, we're in the same position as we were last week. The servo is just rolling backwards and forwards, doing its thing. I will be turning the power supply off because it makes a bit of an annoying noise, so that's just going to stop. There we go. And continue. So previously we were rolling up and down. Now I'd like to extend it. I think the very first thing to do is make it so that we can position the servo according to our desires instead of just having it rolling up and down. So first thing to do probably is to rework this state machine into just a more simple up counter, or a up counter. And the position counter here we will replace with a register, I think, instead. So this state machine currently, it will initialize everything at the beginning, and it will then count the clock cycles. And when the clock cycles are then past the current position, it will set the output to a logic 1, or when it's before that current position, sorry, set the output to logic 1. And then when it's after that position, but still before the end of the... Oh, sorry, thank you. So when it's past the position pointer, but still before the end of the cycle, it will output a 0. So you get a nice pulse at the beginning, then it'll delay for a while. And then when we get to the end of the pulse, or the period for the frequency, we'll then set it to 0 again and start the down counter. So I hope that kind of all makes sense. Down counter is exactly the same, apart from it goes the other way. And so what we have then, these Tmin, Tmax values are the 2 millisecond and the 1 millisecond. So it'll count up and up and up, and the pulse width will get wider and wider and wider until it hits the 2 millisecond point. And then it will hop down to the down state, and it will get narrower, narrower, narrower until it hits 1 millisecond, and it'll just do that over and over again. So what we really want to be doing now is probably none of this state machine stuff, but the position counter wants to be a register. So as is the best way, I'm going to refer to another applet, which will give us the inspiration, the jog, and the memory jog, to remember how to implement a register. There's a simple function call. Here we go. So it's target registers add. And we're going to do a read-write one, so the host can write into the register, and the FPGA can then read from it. So down here, we're going to grab our register. Let's call it position counter, I think, just as before. And we're going to need to keep the address so that we can write to it. It's a read-write address, and I think we're giving them 32-bit fields. There you go. So that's what it was before. There's no particular reason for 32-bit. It's probably way beyond what we actually need for this, but no harm. We can optimize it later if we need to. And then we need to pass that into our sub-target. So pos count equals pos count, like that. Later on, we then need to set the position. So here we've got a read-write register, which is the address manual cycle. Let's have a look at what that is and how it gets set. So it's just device.write register. So we can call that here. So await device.write register self dot address position counter, and we're going to put it to, I think, 1.5 milliseconds, and the calculation for that is the clock frequency multiplied by 1.5 e minus 3. So e minus 3, like that, and the width is 4 bytes. So the clock frequency is something that we can actually get from the target, but I don't think we can get it from the device object. So we need to store it on the applet itself. So let's do sysclock frequency like that, and let's grab it here. So self.sysclock equals target dot I can't remember what it is. It's here, look. Target.sysclock it is the same thing. Great. Okay. So that should write the register, position it midpoint, and just let it go on from there. Let's see what happens up here. We need to rework this a little bit. So we have the position counter is actually something that we're going to feed in as part of the init arguments, and we need to keep that. And then instead of making it a signal, we actually just want to use the existing signal which is being created for us. So I'm just going to quickly do this, pos count, there we go. And that will redirect it. The state machine, we can get rid of pretty much everything, I think. I believe that the counter, the signal, will default or initialize to 0. I think just to be sure we can put a default in here like that. So we can get rid of the upstate. We can then just use the upstate, get rid of the init state and then just use the upstate. So each clock we want to increment the position. We need to rework this slightly. So as it's before the position count, well, it's before the T cycle, so that's going to be the 50-ish hertz, I think it is. And then after that, we need to do else m.d.sync cycle counter equals 0. Then in each of these, we need to increment it. So we can come and tidy that up again in a minute. All of these, I think, can just go away then. I don't think we need them. Okay, so that's a very simple PWM output. Can we optimize that briefly? I think if we go with if cycle count is greater than equal to psych, we can reset it to 0. And in an else block, we can then say, are you before or after the position? And we can actually make that into an n.d.com. So out equals psych count is less than pos count. And I think that's even better. Look at that. The combinational logic will default to a 0. So we're setting it expressly here. But while it's in the if state, it will be a 0. And that's kind of okay, I think. It will get to the end, it will already be 0. It'll be 0 for an extra clock cycle, and then it should go back to 1. So I think let's see what happens if we try and run that. Should, no, not default. What might it be? Init, perhaps? See if there's anything over here which gives it away. Oh, is it reset? Perhaps. I don't think it's in it. Let's give it a go. No, let's try reset quickly. That looks happier. You can't put a float into bytes. So Python is very good, very good in inverted commas with types in that it's gently, softly typed. So here, where we've done this multiplication, what we've ended up with is actually a float. And that obviously doesn't go into an integer field very well, or an integer register. So to fix that up, let's just take this value out, and let's do pos count equals integer value of that, like this. Pos count, and there we go. Let's try running that. That seems happy. So if we turn the power supply on, I think that servo should snap to the midpoint. Oh, maybe not. Maybe it's already there. Might be the point which we need the scope on again, isn't it? So let me just grab that quickly. Didn't prepare it because I was being a bit rushed. Here we go. Here's the scope, and I'll need some extra wires. I need to go from pin to pin, like that, and then I'll also need to go from pin to not pin. Okay, blue. I haven't got another green one handy. And I'll need to get the NC up and running as well. So hopefully you can see that. Okay, there we go. Great. Okay, let's just get this all connected quickly. We're going to need use this row and pop that into that row as well. Can't quite see that. Not too interesting. That then goes into the servo. Wrong wire. Need another pipe. Okay, I'm going to steal power off screen or off camera, just from the power supplies connector. So this is going to be the ground reference that everyone's going to share. And then I'm just going to hook the scope up to this green wire. And we should get something. We do, it's just high, interesting, okay. So if I show you the scope, just a logic 1 there. Okay. Okay, so if we come back to the code, there's got to be a reason. Let's see what's going on. So we're writing the position count with this value here, and that's 1.5 milliseconds. I think we can just print it out quickly, just to be sure. So let's do that. And then up here, the position count is going to be, looks okay. Ah, we're not resetting these. Oh no, we are resetting the cycle counter. Okay, that's a bit unexpected. Run that again and just see what we get out of the position count. That's 72,000. If we put that through a calculator, we've got 48 megahertz clock. Divided by 72 is 666. All right, 48 megahertz divided by. Yeah, so that'd be. My brain is failing me. What would that be? Let's do 48 megahertz. So 1 over 48 megahertz is that times 72,000 would be 1.5 milliseconds. That's exactly what we're asking for. Okay. Sorry about my brain there. So the cycle counter starts at 0. Oh, we're not incrementing it. Honestly, MD sync cycle counter equals cycle counter plus 1. Okay, that should be a lot better. We then grab the oscilloscope as well. There, look at that. There's the oscilloscope. Get that onto screen quickly. There we go. If I do some measurements, we've got 1.5 millisecond on a 19 millisecond period. 19 milliseconds is, I think, or 20 milliseconds there pretty much is going to be e minus 3. That's 1 over, yeah, it's 50 hertz. That's fine. And then you might have heard, but the servo has also snapped into its middle position and it's holding that, so I can apply quite some force. That's, you can see actually the noise introduced on the scope when I press on that on the bottom there. But never mind, we don't care. Okay, so if we come back, we've set the position to 50% or 1.5 milliseconds, but it'd be quite cool if that was an argument that we could set, or even better is if this was a socket that would listen and it would take in positions that we could then just apply to the servo. So I think I'm going to skip the argument and we're going to go straight for a socket. If we have a look at the UART applet again, we can see that it can operate as a socket. So you can set up the UART applet and then connect to it using Telnet or just Netcat or something, and you can then actually interface with that UART. So what we can do here is just copy that. And Glasgow has built-in server endpoint. There we go. So we can just start a server and get data out of it and put data back into it. Hi David, nice to see you. Thanks for joining us. We're playing with servers again. I'm not sure if you saw the vote. Right, so let's see. Do we need to import anything for this to happen? Doesn't look like it. So we need to add some arguments. You might have seen that just here. So on the add interact arguments phase, we can add the server bits. No worries. Yeah, so the vote was between more Servo playtime or a Nintendo Game & Watch, which arrived earlier today. I've been tempted to for a while and figured I just would. Right, so we're going to add the P socket in basically exactly the same way as they're doing here. Connect to a, I don't know, servo, connect servo to a socket, that's fine. Yep, great, I think that's done. And then async def interact, we're going to have to fill in a second. And that we can use, just use this prototype quickly. What am I going to put in there? So we need to device.write and interface. We get the device, don't need that, so let's just do this. There we go. Yeah, let's put the interface back in, sorry. Okay, now we're going to set this to the midpoint again, 50%, just as part of the start procedure. And then we're going to open up a socket which you can connect to and send messages to it. So to deal with those sockets, you obviously need to accept connections and everything. But I think that is all taken care of by this server endpoint for us. So if we grab that, so we're going to use args.endpoint as a socket, and I think we can just call receive on it. So let's do endpoint.receive, just like this is doing, in a while true. Copying is the best way to get started with things. Right, so that's going to receive data, and then it's going to write out the UART. So we're not a UART anymore. So let's... Oh, apologies. Please feel free to ask questions, by the way, anybody. Happy to fill in any details that might be missing. So a bit confused about this. Will your servo control and the UART peripheral run both on the FPGA simultaneously? They will not. I'm just using the UART applet here as a template or a guide on what functions are available, what classes are available to instantiate, that kind of thing. My brain's not so good at retaining this kind of information, so I just I reach out to things that already exist and I just copy bits here, copy bits there, tweak it and make it work again, kind of thing. If I was super familiar with the Glasgow environment, I might be able to just write this off the top of my head, but that's not something I can do. So today we're just going to be working on the Servo applet using other applets at the moment, the UART one as inspiration. In terms of can the UART applet run at the same time as the Servo one? No problem, yeah, no problem. In terms of can it run at the same time, that's something that we want to have as a feature, being able to run multiple applets at once, but it's something which we can't currently do just yet. So there's no way at the moment to run multiple applets. Okay, so if we carry on, here we've received some data. It's going to try and write it to the UART, but we're not a UART, so we need to rewrite this. And I think what we could do is just accept lots of data, and why don't we try and make just a really simple text-based interface. So you write like 50 would be 50 and then press return, and that would be 50%. And you could write 0 return, that would be 0%, and that would then calculate the 1 to 2 millisecond period and apply that to the servo. Will the UART be accessed over USB or directly as a serial device? So the Glasgow has USB to the host here, and then these pins can basically do whatever you like with the applets. So if it's a UART, for example, you'd have a transmit and receive pin on here, which you could then connect up to your device. And they would be raw TTL UARTs. So you can set them to 1.8 volts, 2.5, 3.3, 5 volt, whatever you wanted. And then that would communicate with your device under test, whatever you want to call it. And then on the PC side, you connect via USB and you run the Glasgow software. And that will then see the UART interface from that point of view. So will it be accessed by over USB? Yes. Will it be accessed as a direct serial device? Kind of yes as well, if that makes sense. The Glasgow sits in the little position where an FTDI chip might do for like Arduino use them quite regularly to do the USB to serial bridge. But as with Glasgow, you can reconfigure it into sort of almost anything you like. So in this instance, on the right-hand side, that would be a UART applet, but on the left-hand side, it's a servo applet. So you're no longer communicating as a serial stream with another device, but you're actually just sending the pulse to the servos to sort of give their position command. I hope that kind of makes sense. Okay, so carrying on, we're going to bring data in and just make the data bigger and bigger and bigger, I think, as just an array of bytes, basically. And we're going to then again strip it on the first carriage return or new line, take that number, convert it to a number, and try and put the position out, and then strip it on the next new line, etc., etc. So what we're going to do is data equals an empty array, and we're going to then an empty string, sorry, let's put that as a string, much better. And then we're going to just add to the end of it. And here, now that we've got some data, or hopefully got some data, we are going to then try and do something with the string. So in Python, you can look for a new line. So trying to remember how to do that off the top of my head now. See if I can grab a browser and we can just go searching, because that's the best way to do it. So Python string pydocs, there we go, 3.9, fine. Search, find, no, index of, index, Python string index. Yeah, so that should, I don't know why that wasn't coming up, but string.index should tell us where it is. So in here, we're just going to do, let's do new line equals data.index, and we're just going to go for a /r, maybe a /n for now. We're on a Linux computer. We can tidy this up later and make it all work nicely. If NL, what's NL come back as? Raises an exception, so if we can try this except, what's the exception? Probably a value error, is it? Python string.index. Why did that not come up? On the real Python documentation, here we go. Index. There we go. A value error. Okay. So except value error, and we're just going to ignore that, so just continue. Now we can split the string, so we're going to make it, what do you think? Let's do the position text equals data until the new line, and data then is data from the new line onwards. We can probably get away with new line +1. Just to help us debug this a bit, I'm going to print in here data, and I'm going to then print the pos text and the data as well. And that won't do anything with it, but it'll just chop off the position each time. So let's see if we can run that and see what it does. P operation is not defined on line 89. This will be a copy and paste type issue, won't it? There we go. So P operation is there in the what's it called? In the UART applet. So we're going to just change P operation for parser. There we go. Parser has no object. Add parser, does it really not? Add subparsers. Subparsers, P operation. If that'll work. No, that's not going to work. Right, sorry, we can just pop it in there, like that. There we go. Should work. No. Server endpoint's not defined. Right, where does server endpoint come from? I think we need, there we go, support endpoint. So let's pop that in here. There we go. So we need to give it an endpoint. So let's say localhost. Actually, let's give it a Unix socket. I think that'll work. Sock. What's gonna happen? Looks happy. Oh, permission denied. Why did that happen? Okay, let's look at the interact socket. Here we go, server endpoint. If we grab that, oh, whoops, we're in a really bad place for doing that. There we go. Oh, listen as either Unix :path. So we need to not have the slashes in there. Unix sock. There we go. Okay. And now we've got that socket there. So if we do netcat minus u for Unix socket sock, and we can then put in hello. Let's do hello /n123/n. That didn't work because is capital U, is it? It's not there on the screen. Yeah, it is. There we go. Can only concatenate to string, not a byte array. Okay. So this is a byte array that we get in, which makes sense. Happy with that. It's not what we want to deal with, so let's put that as a string and do string around that. I think that should deal with it. Oh, no. Converted it to string and then added the string of that. Right. Is this going to work better? That's probably going to complain as well, isn't it? String has no attribute append. Decode? Yeah, okay, let's do it. D in equals that. So data dot plus equals d in dot decode and UTF-8, why not? Thank you, David. Should hopefully get us around it. There we go. So position text is hello, and then we've got another one, and it's now blocked on the socket, so that's not what we wanted to do. Break. Thank you. What we want to do, I think, really is in the value error, we want to try and get some more data. So let's try that, I think. Because it failed to split it, so it's got nothing else to do. Therefore, let's try and get some more. That's a bit ugly in terms of nested try excepts in one place. What we can actually do is... I think let's just leave it for now. I can tidy it up later. Right, here we go. So we go hello 1 2 3. And L is unreferenced. And L. Oh, I see. Okay, so if it's a cancelled error, we can just continue. We don't need that try. Yeah, we do. But we want to always continue. So pass that and continue that. There we go. There we go. So we have the position text is hello, and then the position text is 1 2 3, and then position text is just empty. because we've split it on the new line, but there's nothing left. So we need to handle that, I think. Go away, and then so if pos text length of pos text is 0, continue. So we got nothing to do. Like that. There we go. Position text hello. Position text 1 2 3. And if we get rid of this here string, we can just say hello 1 2 3 testing blah blah blah. So that's cool. Happy with that. And if we do really quickly, I don't think we'll ever be able to do it right now, but if the Python application is busy, you might find that it receives one packet with both strings or both lines in it. And that's basically what's happening with the here string here, that we're giving it multiple lines at once immediately, and it's then doing stuff with it. So we can give it 456/n. There you go, so it gets all of them. And if we were to give it without the final /n, you can see that it does get a position text, which is, it has got a /n on the end because the here string gives it one. What we can do instead then is just echo -n, hello, let's do -en, hello /n, 1 2 3 /n, 456 no /n, and pipe that into netcat. And then we get, there we go, so we get the hello, the 1 2 3, and then the data is an incomplete line, so it doesn't deal with that yet. Cool. Okay, that's nice position to be in. So now that we've got the position text, we want to decode it into a value of 1 to 2 millisecond pulse. So we're going to take the pos text and take it into a pos float, for example. Pos float with an A in there and a T, honestly. Okay. So float pos text, and this could very well raise an exception as well. So we're going to try accept a value error, I expect, and just maybe report an error. So just print error. The string that we've got here, so pos text is not a float, and we can then just throw it away. Continue. Okay. Don't really need to test it right now. I'm pretty confident that's going to work, but it's going to say, there you go, hello is not a float, and then it's going to take 1 2 3, and it's going to just get stuck on 4 5 6. Yay. So now what we want is 0 is going to be a 1 millisecond pulse, and 100 is going to be a 2 millisecond pulse. So what we could do is scale a 1 millisecond value, or instead we could map between them, but I'm just going to be lazy. So pos val, I'm going to put it as is equal 1 plus, and then we're going to take 1.0 times pos float. So that's going to give us the 1 to 2 millisecond pulse there. Just print that out just while we're working with it. And then this is going to be pos value, or val. And then finally, we need to convert it into a number of ticks. So we can just do exactly what we did previously. So up here, we've got the calculation. And we're going to convert our, so sys clock frequency is about 48 megahertz. And we're then going to convert the pos val into a pos count. And finally, we can then write it to the register. So pos count. And again, just as we're doing up here, we can then write that out to the register. And that should make the servo move. Now, what this can do is snap the servo, or snap the waveform into that value. So the servo is going to move as quickly as it possibly can. And it might be interesting to just watch the current draw on the power supply down here. And it might surprise you if we can get it moving quickly enough. Okay, so it's at the midpoint. I've got the scope running. Can I just quickly get the scope on screen so you can see it while we're typing away, do you think? Oh, golly, sorry about that. So let's just add 1 second while I do this. Display capture, no, not that. Window capture of the scope. Okay, if you can all see that okay, I'll just put it there. Okay, so what we're going to do now is connect up to the socket. You can see the servo just about in the little screen down here, and you can see the scope just above it in that window as well. I'm just going to resync that. So I'm going to pause the video. There you go. Get it going again. I found out how to bring the latency right down on that, which is kind of cool. So if we go for 0, it says pos count is 48 million. That's not right, is it? If we go for 100, too big to convert. Okay, so we got something wrong there. What have we done? Let's have a look at the output values. I'm going to add. What am I going to do? Just add some space in here, I think. And here as well, just so we can see what's going on a bit better. So you give it a 0. Give it a 0, and it says 40 million. That is, so 100 is then squillions, and it's too big. The issue here, I think, is that we are multiplying the wrong thing. The pos float. Oh, I know. It's because we are giving it. We're expecting a 1 to 0 value, not a 1 to. 0 to 1, not a 0 to 100. So let's rework that, I think. And if we go for 0, we should get that. And if we go for 1, we should get that, which is also wrong. Yeah, that is wrong. Pos val. Let's put the 1 here. 1 plus pos val. Let's get rid of the 1 plus here just to help reduce the confusion. 1 times that divided by 100.0. So that should give us 0 to 1 based on a 0 to 100 input. That's 0, 100, 0, and 1. And if you go for 50, that's half, 25. Yeah. Okay, that's better. Now the pos count is way out. And that is for some reason. So we're not doing milliseconds, so that should be times 1e minus 3. There you go, we're doing 3 seconds instead of 3 milliseconds. Okay, how's this going to go? 0. Woo! 100. Look at that. Brilliant. And 50, 25, etc. Now what you can see down here is actually not as impressive as it would be if you were looking at the output or the screen directly. But this can go shockingly high because it's going so fast. So one of the reasons, or one of the things that I'd like to do, is to basically reduce the speed of movement here. So we have a target, but we are aiming for it. We're not snapping to it, if that makes sense. And that's something we can do in the FPGA, which is brilliant. If we were to do that on the PC or even in software on a micro, you might get a bit of jitter in there in terms of how it moves. It might sort of get an event, say, every 100 microseconds instead of, or plus or minus 5 microseconds. But if we're doing it in the FPGA, we can be really precise about when that event happens. So in here, what we want to do is we've got the position counter, and that's what we're aiming for. We've got the cycle counter, which is where we are right now. But I want to put a sort of an interim value in there. And I'm gonna use the same name just for now, I think. No, let's not do that. Let's do target count equals self.pos count, just to remove the ambiguity there. We're going to do a position count of 32. Reset is going to be 1 plus, let's do t mid. (1.5e minus 3). There we go. So that's going to reset to T mid, which is a midpoint. And we're then going to have the position counter, which is our, the target counter, there we go, which is our target. So we now need to alter this slightly. We go in the else, so while we're counting up, or while we're waiting out the period. No, let's not do it that way. So in the reset, so at the end of every period, we get the new target or the new position value. If you were to change this partway through, then what you can actually get is artifacts where you have two pulses potentially, or a shorter pulse or whatever. So if I had a 1 millisecond value programmed, and I then change that for a 2 millisecond value, you might find that the counter actually passes the 1 millisecond point and the signal goes low. And then, so it passes the 1 millisecond point, signal goes low, and then you get a little bit of time and you get the new value all of a sudden. So the signal then goes high again for the rest of the period until the 2 millisecond point at which it goes low again. And you actually get this double peak or double pulse or whatever you want to call it. And that's something to avoid. So what we're going to do is reload the counter, the position at the reset, at the end of the period. So if we do it here, so first of all, we can just do md sync pos count equals target count. So that's solved the problem for now. But now we actually want to introduce a speed control so that it will slowly move to position instead of just snapping there. What I'm going to do is just very dumbly, if the target is below the current position, I'm just going to decrement the position until it reaches it. If the target is above the current position, I'm just going to increment the position until it reaches it. So m.if pos count is less than target count, target count, then we need to increase it. Pos count, let's do +10. So else if the position count is greater than the target count, we want to do pos count equals pos count -10. And that should, if we move by 48 millionths of a second each time, then we should get probably quite slow movement. So let's just give that a go. Not going to be perfect by any means. There's an issue I can already foresee, which I will talk about if and when it shows its head. Otherwise, I'll just mention it. Right, okay, so here we go. If I go for 0, it is moving, but you'll have to take my word for it. Watch that for a second while I can't do that because, I can. That's okay. So the FPGA will keep running if I break it. Yep. So I'm gonna have a play in the background. I'm gonna make the 10 into 1,000 instead. And I'm gonna reload it. So you can see it, that's definitely moved. I can hear it, but you might not be able to. Okay, so I've changed it for 1,000. That's exactly what I wanted to talk about. You can't see it. You can probably hear it. And you can definitely see it on the scope. So if I show you this, you can see the wiggles at the bottom there. That's noise. And what's happening here is the pulse width is changing by a 1,000th of a. Well, let's just calculate it quickly. So what is it going to be? It's going to be 48 megahertz, 48.6, 1 over that. So times 1,000. It's changing by 20 microseconds, and it's just jittering backwards and forwards. And that's enough for the servo to be a little bit unhappy. If I now swap this out for a 0 value, I'll put you on this overhead camera. It did take a second. It didn't just snap there. So that's much better immediately. But we get this issue where it gets to its target and then it just wiggles there. And that's not good. So let's turn that off because it's annoying. And let's come in here. Now the issue is that we are just wiggling backwards and forwards and we keep overstepping the target. What we really want to do, I think, is adjust this by the difference, or cap it at 1,000. If that makes sense. So how would we do that in MyGen in the actual gateware? Let me think about that for a second. There's a mux thingy we can use. Mux. There we go. I think that might be the oldie name for it. Yes. Leave us hunting. Yeah, exactly. That's exactly the issue I was just describing. That we're just overstepping and hunting backs and forwards over the target. So if we do the difference, so we cap it at 1,000, then what that means is that we'll move by 1,000, 1,000, 1,000, and then the last step might be 120, for example, and we'll hit the target dead on. I just need to remember how to do the mux type thing. Not called mux anymore, and that's annoying me because let's look it up. So MyGen compat guide, I think, will get us. And MyGen, okay, there we go. Not called what I thought it was. Docs. Historical, maybe? Compat summary, there we go. So we can search in here for mux. Oh, mux doesn't have an updated thing listed. Trying to remember where I've used it now. If I can go and grab it. Okay, never mind. What we can do instead is in here with m.if we can do pos count. So if pos count is less than target count, so target count minus pos count, put that in brackets. Not a great way to do it, I don't think. If that is less than 1,000, then m.e.com, we can do the difference, there we go, to target count minus pos count. Else we can do md.com diff equals 1,000. There we go. And we can just put diff in there. And now let's make diff a 32-bit signal, just like that. And then on the other side, we need to do the same again, but it's the other way up. So if, here we go, pos count minus target count. There might be an absolute operator in this, but I'm not going to go searching on stream. So I think that should, put a diff in here. That should do what we want it to do. Let's run it. Turn the power supply on. Oh, no. Oh, there we go. There we go. That was the last applet still running. Okay. So if we connect up to it and we do 0, then it moves, 100, then it moves. Not super pretty. We can see on the scope there's no glitches. It does sound like we're not updating perhaps quite fast enough, but we're limited by the update rate of the servo. What we could do is reduce the 20 millisecond period to, I don't know, 10 milliseconds maybe, see if it can deal with 100 hertz. I think the servo might get a bit unhappy though. Oh, seems okay. Does that come through onto the scope? Let me just grab it. Yes, it has. There we go. 100 hertz. Okay, so if we go for a 0, oh, that's. Ooh, 1,000. Whoops! I didn't range limit. Oh no, it's. Oh, let's come back. There we go. sounds a bit happier. We got more updates per second, so that means that we are, instead of sort of jittering across, we're actually sort of moving a bit more smoothly. Let's also adjust that 1000 to something different. So let's call it rate and put it at 1000. Just replace all of these 1000s. Rate. There we go. And if we change that for 250, perhaps. Is that gonna do the job? There you go. So you can go for 0. Oh, look at that. 100. Nice. Okay. Now, the issue here is that we've got no control over that rate. So I think that's either something that would be quite cool to have on the socket interface, or perhaps something on the command line. I wonder... Let's put it on the socket interface. We're starting to get a bit more complex now. I kind of want this to perhaps take in JSON objects or something like that, so that you can have some other machine system, whatever, controlling the position of potentially a number of servos. Right. So that rate there is, I think, something that we're just going to change right now for a register. I didn't really mention it earlier, but you have, between the Python and the Glasgow, the FPGA applet, between the two halves, you have a couple of interfaces available. So there's effectively a socket-based interface, so you can send bytes across one way or the other way. But you've also got these registers. Registers aren't really intended for sort of the high bandwidth data or anything like that, or really things which need sort of a protocol or control, I suppose. But they work quite well for like configuration values, I guess. So in this situation, what we're doing is we're just putting in the position of a servo or the rate of change for a servo, and for that, I think they're quite good. There might be other opinions out there, but let's go back. So this rate is going to become a register as well. So pos rate. I'm just going to make it 32-bit again because I'm lazy. Have a bit more of a think about it later. I think also if we change the counter here for the target keyword that we were using before, same again here, and we'll add pos rate equals pos, oops, like that. So that's now a register. It's not got a value yet, but we can set it here. Oops, here, sorry. So pos, oh, that needs to change as well, so target and rate. And we're going to set it to, I don't know, 500 seems like a good value for now. It'd be quite cool if we could get like degrees per second or something, but based on the servos that could be connected and the various other bits of, you know, moving variables and everything, I think let's just leave it as a raw value for now. I wanted to change this, so the count needs to become target. Okay, and then back in the applet on the left-hand side here, let's change that for target and pos rate. Misspelled that, there we go. Okay, where do we go now? So that becomes pos target, and we then have, alright, let's normalize some of these words. I think it's getting a bit confusing. So pos target, I'm going to use that here, and pos rate. Just make them local variables so that we can access them more easily. Let's change the target count for pos target. I missed one, whoops. No, I didn't. Oh, okay, sorry, I'm misremembering. There we go. Pos target, okay. And then rate here then becomes the pos rate. Just like that. We get rid of this hard-coded value. Okay. Cool. So now I think we want to add that into the protocol. What I'm going to do, I think, is perhaps suggest that we have the position colon rate. And if the colon rate bit is missing, it'll just use the previous value. So what we're going to do then is take the packet equals data NL, there we go, and change that for packet. Okay. So previously we just, the entire packet of it, or the line was just the data of the position. But now we're going to have the optional colon rate on the end of it. So what we need to do is, tell you what, let's do this more intelligently. Let's, instead of doing index of, which happens here, let's do split minus n one time. So NL now will either be an array with one item or array with two items in it. So if len and NL equals is less than, ever going to be 0? Python 3. If we take this empty string dot split on new line one time, no, it'll be a one thingy array. So if we do ABC, it always gives you ABC. And if I do a slash n on there, DEF, and it gives you the 2. And if I do another slash n, GHI, it bundles the others together. So it splits it maximum one time. That's fine. So if the length is 1, then just continue. Otherwise, we're going to do data equals ln or nl 0, and then the packet equals nl1. So we can get rid of these like that. Oops, I got those backwards. Get rid of these ones. If the packet length is 0, then continue. So that just means that if it's an empty line, just ignore it. Okay, now what we want to do is split the packet into 2 based on a colon, so, or into multiple points based on a colon. So packet parts equals packet.split colon, and I'm just going to split it as many times as it likes. Oh, sorry, yeah, I will hide the oscilloscope. Just do that quickly. Very sorry for blocking your view there. Right, okay, so we're splitting on colons. The first one is going to be the position, so we need 1 count. And if we go, if len packet, actually let's just do split on a colon there. Okay, so if the len packet is 0, or 1 or 0, okay. How are we going to deal with this? The lazy way. That's fine. We'll deal with it more properly later. I can do regex or something. Do regex now. Go on then. Import RE. I'm going to come back to the Python RE documentation. And in here, I can never remember if it's search, which does the entire string, scan through string looking for the first location. No, so match. At the beginning of the string, match the regular expression. So re.match. Okay. The string, so that's packet. And then the regular expression, so the way around. Always get these backwards. Okay, so new line, we're allowing some numbers. And then we have an optional colon, some more numbers, and then the end of the line. And if we give these then some names, I think it's $P name, isn't it? So this is the pos, and then this will be $P rate. Okay. And then we can take a match, and there's something like group ticked, I think. I'll just group tick with no underscore. So if match is none, continue. We can swap that out, and then we can do and at this point we can then address our values. So if what is it? Rate pos. Sorry, if pos in match, then we set the position, and that's going to be a number. We've already declared that, so we can just try and make it a float. If it is a float, then we take it, do the maths, and put it out into the register like that. Let's just tidy this up a bit. So we got the error. That's good. Get rid of all of these. We don't need them anymore. Let's swap out pos for target. Keep our naming a bit better. Okay, pos. So this is then going to be match pos. Oops. And that's then going to be target float. Okay. So if we've got the position, then bring that in. If we've got a rate, then we want to use that as well. The rate is just going to be a raw value, so we're going to try and make it an integer. So let's just copy those. Pos text is no longer a thing. Let's just fix that quickly. That'll be match pos. Okay. And here it's going to be match rate. Right. Rate, integer. This is not target anymore. It's going to be rate. That's actually not a float anymore. It's going to be an int. Rate int. And that's just going to get written straight out. No other calculations to do on it. It's not an int. Okay. Pos rate, target rate, width 4, good to go. Can get rid of all this. Okay, do you reckon that'll work? Don't know, let's find out. Okay, on the scope back, let's bring that back quickly. Okay, so, oh, it failed. Okay, brilliant. Get rid of the scope again. Max frequency error for clock. Now, I had this earlier today for something else I was working on, and I couldn't figure out what it was that was causing it. It seems to be a little bit difficult to get any more out of the toolchain that's behind Glasgow. So I might be having a chat with White Qualcomm people about that. This is saying 43 megahertz fail at 48 megahertz. CD sync clock if 0_I. Yeah, okay. What is the problem, do you think? Start removing stuff until it works again? Just do that. Not ideal, I don't think. Okay, so that worked. So something about these diffs. Put one back in. That's okay as well. Oops. Put the other one back in too, and then is it going to fail? Don't fail. Yep, failed. Okay. The target rate. I'm not going to see it, I don't think, right now. That's really annoying. Okay, what we can do actually instead is, instead of moving it by the difference, we can actually just move it to the target. That probably makes a lot more sense. I think it probably does, yeah. I'm not entirely sure what it is that's causing it or why, but let's just simplify this a bit. So if the position target minus the current position, the target minus position, is less than the difference, the rate that we're allowed, then just move it. So md sync plus equals, just to grab that. So we're going to move it to the pos target, like that. Otherwise, we're going to move it by the difference. So that's kind of cheating. It's a nice little optimization, I think. Oh, you think 16-bit registers might help with this? That's a very good idea. I'm just going to try this quickly. Just sort of snip those bits out like that. Okay. I was working on the, there we go, that's okay. I was working on the frequency counter earlier, and I ran into that same issue. We're in a really unexpected place as well. Couldn't quite figure out why it was failing. Okay, so if we just do 0, it should move there. But it doesn't, and I can hear my little computer whining its fan again, so it sounds like we're probably going round and round in circles. Let's just check what's in each of these points after I've removed all the stuff. Yes, that looks okay. Bring the packet. Yeah, that's a good point. I'm going to print out the match as well. Kind of expecting that it won't ever really be none, I don't think. Putting the packet in, that's okay. Oh, hang on. No, we removed the new line because we split on it. Okay. I'm going to print out the match again second time. And I'm going to just put some space in here so you can see what's going on. I think if we connect up, that's just going to whiz around the loop and we'll see it. Oh, no, maybe not. Okay. Oh, hang on. We're never adding the data. Yeah, we are. Okay, so that's okay. So, oh right, we're doing a split. And we actually want to do that in here. There we go. So if we split it and we have only one element, as in we haven't got a new line yet, try and get some more data, and then start again. That looks better. There we go. So 0. Target must be a string or byte select number, int match rate. 157. Oh, rate is none. Okay, so it's not a matter of whether or not it's in there, it's a matter of whether or not it has a non-none value. So match pos is not none. Turn the scope off again, sorry everybody. Right, match rate is not none. Okay, let's try that. Seems okay. 0. Oh. Servo's not moved. 100. Servo didn't move again. If we do 0 colon 250. Oh, target rate not defined. 162, 162, 162. Oh, rate int. Okay. 0, 100. So those aren't moving it for some reason. 250, 0, 250. That's not doing the trick. Oh, we're using diff. Sorry, we're not using the rate here. So diff is going to be default 0. Okay. Rate's not defined. Pos rate. Pos rate. Okay, and then let's try again. So 0. That's better. 100. Okay, let's bring the scope back up. Not showing loads of information, but the width does change at least. So okay, and if we do then 100 colon, let's do 25. That's nice and slow. Look at that. You can see the width, the positive width here, just creeping up. And if we do 100 colon 100, gets a bit faster. Brilliant, that's awesome. 0 colon 1000. Nice and fast. I like it, I like it. Let's remove some of this debug that we've got then. Make it a little bit cleaner. Yeah, okay. So we've got position and potentially a rate as well. I wonder if next step might be, thank you, yeah, fingers crossed it's coming along. Okay, not too slow for everybody watching. So I'm not sure if the next thing would be acceleration and like a curve. So at the moment, what we've got, I'll just bring the little notepad into screen here. At the moment, what we've got is going from position 1. Initially, we had just smack bang like that. Then we increased or updated it, and now we've got the ability to have a rate of change like this. And actually, we can make it really, really fast, or we can make it really, really slow. And I think it might be nice if we had the ability to sort of accelerate at the beginning and then decelerate at the end. But where that's this curve there, a curve there. But I think that might be a little bit much for today. So let's ignore that one. We're just going to stick with the variable rate changes. But I think what would be cool is multi-channel servo support, so that we can connect potentially all 4 of the servos on this fixture and position them all independently from some network application. I think that would be cool. So let's maybe aim for that. I think what I'm going to do quickly is just make, oops, caps lock on. I'm going to make just a dirty commit, and I'll come back and tidy things up and make a nice commit message later. Okay, so what we have is this sub-target on the left here. Go to the scope again, so we don't need that at the moment. What we have is this sub-target on the left here, and this will take control of a servo. So what we want to do probably is to break it up or break it down into individual servo channels, which we can then duplicate multiple times potentially. So we've got servo ppm output. This is this one up here is the raw pins basically. And then I think if we take a class servo ppm output channel, and this is then going to start showing the real power of Glasgow, because we're able to instantiate and change the gateware by just altering the command line arguments, for example. So what we're going to have is pads, and then control regs. No, actually at this point we're going to have pos target and pos rate. Actually, we can just copy these. Elaborate. So the output's going to be a signal just as before. fact, I wonder how much of this is just going to be rewording of the sub-target. Probably all of it. Let's put that back to, well, let's just make a comment at least, 100 Hertz there. Because that's kind of atypical for servos. They usually go at 50-ish. Yeah, so I think actually that I just take all of this and move it into our new module here. There we go. Now we're going to make use of this module, and we can instantiate it a number of times to take control of one servo each. So we've got the pads, and we can then have the control registers, let's call them. And in here, we're going to want to, for each pad that we're given, we're going to want to break it off with its own control registers and instantiate one of the output channels. So for pad in self.pads, I can't quite remember what these look like, but I think that would probably be the one. Pads. Okay, so we're going to have to rename it from out to like channel or channel count, channel N, channel 1, 2, 3, etc. Let's just do that for a second though. And then in the output, we want to change it so that we've got control registers equals just an empty tuple for now will be fine. Oops, wrong button. There we go. So if we run it, they say pad is not iteratable. Okay, fair enough. Of pads. What other applets have we got where we can draw inspiration? There is the WS2812 applet and have a number of chains in it. So we go for video WS init. Okay. In here you can give it. There we go. So we can give it between 1 and 17. It might be actually 16 output pins. And then each of them is a string of LEDs, and then the count gives the number of LEDs in that string. So then we pass the pads here are iFace get pin for pin in args pin set out. So it's a pin set, and they are the output pins. And that then gives it an array. Okay, so if we dig into that, how does it do it? These pads then come in here, and it puts it into the output module. Pads, so enumerate self pads, just like that. Okay. In that case, I think let's start off by changing our arguments. So we're going to just put that in there, and put that in there. I'm just going to take a copy of them. I have them on the other screen. I'll be referring to it. In here, so we're going to do access add pin set. Add pin set argument. Parser out width is a range of, let's go for 1 to 8. Required is true. If I spell that right, R-E-Q-U-I, required. No. Yeah. That's all right. And then in here, we take pads equals an array of get pin for pin in args pin set out, like that. Stop that out. There we go. So that was pads for pads. Okay. The pads here is like that. So in the other applet, they enumerated it. Okay, so what they did here is they actually got the index into the output, and the output is then dealt with here as en masse, basically, because it's to produce a 2D screen rather than what we're doing, which is a set of independent things, basically. So we don't need to enumerate it, but we can print it, just quickly run that. What it does, we need the pins out now, is 1. And we could give it, I think, a comma separated value or list there for multiple pins. So if we do 1, 2, we get 2 pins, there you go. They're coming out here. Oops. And you can see that each time we change which pins we wanted to use, it's rebuilding the gateware, and it will actually then sort of instantiate more control modules as is required, which is really, really cool. So flexible and dynamic. Okay, now we need to pair up the pad with the control registers. So we can use zip for this. Self pads, self.control regs, like that. And what we can do then is the first pad we get matches up with the first control registers we get, the second, etc., etc. And in here we can then go and do m.submodules plus equals servo ppm output channel, and we're going to give it the pad singular. So let's reword that on the left over here. Self.pad, pad singular, pad singular. Okay, I think that's fine. Let's just leave it. This out T might need to be reworded in a bit, but we'll get to that when we get to it. So we have the pad, and then we're just going to do. Actually, let's just do this nice with names and everything. So pad equals pad, and then we've got the pos target equals control register 0, and pos rate is going to be control regs 1, like that, and we're done. Okay, so that will instantiate them as we need them. The issue here now being that the control registers, there are actually only, well, we're giving none of them, but we've only instantiated one set of control registers. So what we need to do is rework that a little bit, but for now I'm just going to put in just the first one, and we can just for now we can work with a single register. That'll be the position target and the position rate, and that's then a tuple of tuples, which is a bit grubby, but we'll come back and fix that up in a minute. I suspect it might blow up because of this, so we'll try and run it with a single pin and just see what happens. It has no attribute submodule, I think it's plural, isn't it? Submodules. Control reg is not defined, 85. That's self dot. Super has no output, out T. Okay, exactly the problem. Now this pad, I think we can just do that, is that right? No. What do we actually see here? Face get pin. Let's just have a look at that. So we did it earlier. Print pad. Oh, it's a tuple. Okay, sorry. Okay, so what we have is pad there and control regs there, because we used zip. What zip basically does is if you have two independent arrays or lists, it will then interleave them so that it takes the first element of one and the first element of the other, puts them together and gives you them, and then it takes the second element, puts them together, gives that to you. So what we've done is we're taking the list of pads and the list of control registers, we're kind of merging them and then giving them to ourselves one by one as is appropriate. So actually it's not self dot there. That was correct. Okay. There we go, so it's running. See if it's still going to work. If we watch the servo, 0, it's already at 0, I think. So let's go for 100. Oh no! Look at the scope. That's an unhappy scope. Got a just a low signal on it, and nothing changes that. Okay, so back to the computer. Control register 0, 1. And we've got the target and the rate. Target rate coming through. Okay, there. Okay. Pause target, pause rate. So why is that unhappy? The print pad. And I'm going to print the control registers too. Something wonky going on here. Oh, have I turned power supply off? No, power supply is still going. That wouldn't affect the output actually either, so yes, different thing. Okay, the scope's still showing just a flat line, unfortunately. And if we do any input, it's still just getting a flat line. So, what's the problem here then? Get rid of that, that's stale now. Min, max, I'll probably come back and use them in parts so that the, when I did 1000% earlier and it just went way off the scale, in parts so that doesn't happen again. It's actually then limited in the FPGA, but I'll do that later. I'll make a little to-do. So the position counter starts in the middle, starts from 0. Control registers. Oh, that's a single signal, is it? Odd. I was expecting that to be multiple signals. Let's do a list of lists, just to be clear about it. Pause target, pause rate. That's better, I think. Got 2 signals coming through at least now. Still no waveform on the scope though. No, okay. What I'm going to do is try and prove this out. So the output currently is here. It's currently variable, so I'm going to do MD combinational out equals 1. And I'm just going to hard code that for now, and hopefully we'll see that come out of the scope. So that'll prove out that the pads are okay still. Oh, am I using 1 instead of 0? Should I be using a 0? I think that might be what it was. Oh dear, apologies everybody. Yeah, so the first pin is A0, not A1. That's a rookie mistake. What do you reckon? Yep, that's happy. Cool. Okay. And then we can move it. So if I put you down on there, we can move it to 0. We can move it to 100. Need to resync the camera, don't I? Again, freezes. And then get it going again. Okay. Right, so 0, 100. There you go. It's a bit better. It's not perfect, this camera. Still a bit of latency in there. And we can set it a bit faster as well, just like before, I think. 100 for 1000 speed. Yeah, that went faster. And 0 for like 25 speed. Going nice and slowly. Brilliant. Okay. Now we need to come back to the computer and just figure out the building of all the registers. Yeah, so let's just do the building first. We need to build this list of lists, basically. So for pin in args.pin set out, let's do that. Control registers, there's nothing, empty list, sorry. And in here, oops, we want two registers, 32 bits, and the first one is the target, second one is the rate. And we're going to put them into, let's do the address of, like that, there we go. So control reg plus equals, yeah, that'll work, pos target and pos rate. And we also want to do self dot, let's just call it self dot reg is, like that. Registers, double underscore on there again. It's an empty list. Okay, so we can just put then in here control registers. And now we need to rework this. So we want to initialize them all to their sort of known good values. So for registers in self.registers. The first register is going to be the position, and we're going to just use the 1.5 milliseconds against the midpoint. And so we do register 0, that's that value, register 1, that's that value. Okay, looks alright. And now, what we're going to do is we're going to extend this protocol slightly. We're going to say the first argument is the servo index. And that's going to be a numeric thing from 0 to whatever. So we're going to have index colon position and then an optional colon rate. First things first, we need the index, but we've already established that in the regex itself. So we can do, we actually don't need this one. We can just make that a given. So the target index is going to be an integer of match index, except value error. And in here we're going to say if it's not an integer, then go away. These errors probably need a bit more description then, don't they? So the index, the position, and the rate, just so you know what you're actually talking about. Okay, now the register rights, we're going to have to grab the appropriate registers based on the index. So if what we're going to do, registers equals self registers target index, and just a really lazy way of validating that input. What's it going to be? A value error? No, I think it'll be something else. If we do an array of no elements and we try and get x1, index error, of course. Yeah. So we can just say if there's an index error, then it's not a valid number. Continue, and let's put that in there as well. So index thingy target index is not a valid servo. Like that. There we go. Then here we just do register 0. We can come back and name them at some point, that'd be quite nice. Maybe put them into a dictionary or something, I don't know, let's come back to that later. Let's do it now. Nothing like confidence, or what's the word? So in here we want the target is going to be that. And then we want the rate is going to be that. That's then a dictionary. Do the same thing again here. So target and it's a dictionary. A list of dicts. This is going to be the target, and this is going to be the rate. Oops. Now I'm not sure if registers are going to sort of go out of style, or what's the word, like if we're going to run out of space for them. I think we're probably going to be okay, even if we go for 8 servos, so that should be good. So we can just go for the registers in here, like regs, like that. Self.regs. And then in here, where we distribute everything, we can say regs equals regs. It's okay, rename that. And then finally, when we use it, instead of saying that, we can say regs target and regs rate. There we go. Okie dokie. Much nicer, isn't it? And we should, in a second, be able to connect a second servo up. What do you reckon about that? Just make sure this works still. Oh, string indices must be integers. Self-register, line 48. Self-registers. That was unexpected. What is self-registers? We control registers. Let's just call them registers. Then find and replace. I think that should be okay, shouldn't it? That should be a list of dicts. Oh, it's not. Is that a funny that I didn't know about? That's better. Ooh. Oh, of course, because when you iterate over a dictionary, you get its keys by default, don't you? That's an unexpected one. There you go. So we're going to append each of those. Right. What do you reckon? Place your bets. Kiera 0, line 132, 132. Oh, right, yeah. So this is going to be the target. This is going to be the rate. You've all gone very quiet in the chat. Hope it's not too boring. Oh, it worked. It worked. Okay. Let's get the scope back. There we go. So 0. Oh no, because we need the going to be 0:0, isn't it? There you go. 0:100. 0:025. Slowly. 100. Ooh, a bit faster. Go for 0, 100, and then I don't know, 2000. Really fast. Nice. Okay, so if we do 1:025, nothing happens. It says index 1 is not a valid servo. We just do 0. It's interesting. You don't get error messages. Probably failing out somewhere without an error, maybe. Oh, that's not expected. Oh, continue with none. Okay, let's just put a print in there. Error invalid packet. Nice. Okay, so second servo time, I think. Let's see if I've got the wires for this. 1 second. Okay. We should be good to go for a second servo. I'm going to find the one labelled number 2, which is this one. I've got blue, it's going to be the ground or 0 volts. That. And then yellow is going to be the supply voltage to it. Like that. And then finally purple is going to be the signal. Like that. Okay. So if I rerun the applet, we hopefully should be able to give it 0 and 1 as the pins. Like that. Seems happy. Oh, 2 servos live. Sure, I just saw 2 move. So if we put 0 to position 0, there you go, and 1 to position 0. Yeah, look at that. 1 to 100, 0 to 100. Nice. How many more wires have I got? Yeah, I think I can go all the way actually. Let's do all 4 servos just to prove it out. Right, so we got purple, oh sorry, orange. It's going to be servo 3. Well, it's getting a bit short. Orange is servo 3, and then we've got yellow, servo 4. Kind of like that, servo 4. Whoop. And then the power all connected up. Messy now. Last wire. Oops, I missed. Okay. There we go. We should have all 4 servos powered and wired up. So if we restart the applet and we do 0, 1, 2, 3 as the output pins, that looks okay so far. Building, building, building. There we go. Everyone sprang into life. Let me just turn the scope off quickly and I'll show you the... yeah, so here we've got pins out 0, 1, 2, 3. And everything sprang into life, which is cool. If I show you top-down view, and I'm going to do 0 to 0, 1 to 0, 2 to 0, and 3 to 0. And what's really cool about this is now that we've done that, let me just grab that and resync the video quickly before we do this. Okay, so now that we've done that, we can give each servo its own rate of movement. So I'm going to say 0 goes to 100 at a rate of 50, 1 goes to 100 at a rate of 150, 2 goes to 100 at a rate of 250, and 3 goes to 100 at a rate of 500. So now we can go 0, 0, 1, 0, 2, 0, 3, 0. There we go. Oh, mistyped. That's really cool. I'm happy with that. Maybe some kind of addressable index. Let's just have a look at that quickly. So if we have, let's put the index. So currently it's allowed to be a 0 to 9. Let's do the word all or 0 to 9. And then we're going to need to rework some of this down here. How are we going to do that best? Yeah, okay, so if target match index is all, then the registers are going to be just self registers. Otherwise, we're going to try and get a specific register. And to do that, we're just going to say, make a little list of the registers only including one, basically. Here, then when we come to write it, we're going to go for reg in registers, write that. And then we're going to do the same thing again here. So for reg in registers, write that. Okay, so now we should be able to do kind of an all call type thing where we say all servos move to. Very nice. And do you see how quick that was? We didn't actually rebuild any gateware. We just changed the Python application. So that's really cool. That's kind of where Glasgow just shines. Okay, so if we do 0, 0, and 50, and I'm going to do 1, 0, 150, 2, 0, 250, and 3, 0, 500. Now if I go all colon 200, 100, look at that, that's gorgeous. Chuffed with that. All colon 0. Oh yeah. All colon 50. Yeah, that's nice. I'm happy. Tiny. I'm happy with that. Okay. There you go. So let's just do a little bit of tidy up, I think. Get rid of this. I might rework some of this a little bit later. I'm going to get rid of the scope again. Sorry about that. There you go. I think most of that's probably okay for now. Not super comfortable with the way we're handling the need for more data. I think I'm going to reword this. So if data.index new line equals, oh, what was it? I can't remember now. Python string index value error. Okay, so what we're going to do then? We're going to do try we can do if a new line is not in data. That'll do. Nice. We can do this. We can then get rid of that continue, which is kind of cool. I think the async IO should probably break instead of pass or continue. That's going to add the incoming data to the list. And then straight away we can say C question mark? This is Python. Is that what you meant? Back hit data equals data split on n1. I think that'll work. Oh yes, yeah. So this is Python. We're playing with Glasgow. That's fair enough. Sorry, it's a bit small on your phone, I imagine. We are playing with servo controls from Glasgow. Actually, what we need to do is we need to continue again if there's no new line in data. So let's just leave continue in there. I think it's a bit better still. That's nice. Cool. Okay, so we can now just try that again. So I'll do all to 100. Yeah, and all to 0. Yeah, brilliant. All to 50. Cool. That's a bit better, a bit tidier. What we've then got is we can get rid of that printout there. I think the registers default values are all okay, and the creation of the registers is kind of alright. I'm not so unhappy about that. I might come and fix it later, though, you never know. I kind of feel actually like it would make more sense to give the pins and the registers in a thing. So how do we do with that? Let's reword this so that the control registers list is actually servos. And in the servos dictionary, we give it the pin as well. That works, I think, nicely. And then we can say star servo. Servos. No, we can't. Servos, there we go. In here, it's no longer, oh, that's a channel, there we go, sub-target. So it's no longer pads and registers, it's just servos. And here, we're no longer doing a zip, we're just doing, just do servo singular in self.servos. And the output channel, so we're going to do pad equals servo pin. We're going to do reg target, servo target, and reg rate is going to be servo rate. Okay. That's better, much better. Keep that up so we can refer to it and come to the panel. Here we go. We're going to have a pad, we're going to have a reg target and a reg rate. Reg target. Okay. And then these can just switcheroo. Reg target and reg rate. Okay, I think that works. These could probably be smaller. Could be smaller. Let's come back to that in a second, I think. Does that still build? Probably have to redo some gateware. Yeah. There we go. Got a good pulse train coming out of the Glasgow. There we go. And if I show you that and do just a simple all to 0, all to 100, 1 to 100 at rate, I don't know, 50, and then do all to 0. And yeah, brilliant. Still working nicely. And this like duration, this fade or movement, whatever you want to call it, is completely under control of the FPGA. So I can actually completely kill the application. And in fact, it's still moving, and I'm not in it, not running the application anymore. There you go. Yeah. Okay, so what we have here is a question about the size of these registers. 32 bits is actually pretty massive. 4 billion ticks of a 48 megahertz clock is quite a long time. What we now know is that we need to be able to refer to a period of up to, let's say, a second, which is 48 million. So we can just type in 48 million in here, and we get, that's 1, 2, I miscounted, 1, oh, we can just go here, 1, 2, 3, 4. So a second is actually big. If we're going at 50 hertz. Say we're going at even 25 hertz. We can go for 48 million divided by 25. You can get away with 24 bits for sure, I think. So we can just turn that down a bit. See how that goes. Bit of a slow build. There we go. Okay, so if I do the same simple test of all to 0 and all to 100. Happy. Okay. Now, one of the issues I had earlier was I did all to 0 and then I did all to 1,000. And it did it, but it did it way past the end. And if you look at the waveform here, it's actually 6, 7, 8, 7, 8, 9, and there you go. It's no longer a pulse train anymore. It's just full, locked up, whatever you want to call it. So what we need to do is a little bit of validation in here. Target float, here we go. It needs to be between 0 and 100. Otherwise, that's not okay. So if target float is less than 0 or target spelling that wrong. Target float is greater than 100. Print pos is not between 0 to 100. Okay. I have actually just realised that the regex here will not accept floats. So the position is allowed to be a floating point number. And so to deal with that, let's just put in this. There we go. So previously, if we typed in like 50.5, then it wouldn't take it. And I'm going to say we can have up to 3 decimal places, because otherwise you get silly. 3 is already a lot. That's what, 100,000 positions, which the servo probably can't resolve anyway. That should take care of it here. The other issue I wanted to take care of it was inside the FPGA, so let's just give that a good go. There we go. And again, this is only Python changing. The gateway is not changed at all, so it's really fast. So if we go all to 0. Oh, missing bracket, unterminated thingamajig. Ding, ding, ding. Okay, what have I done there? I put a escape on the closing bracket. It's kind of annoying the way that Vim and other things sort of escape different stuff in regex, so you're never quite sure what you're going to get. So if I put all 0, invalid packet. All 0, invalid packet. Okay, let's do all, oops. Oh, the connection lost and then it died, okay. All 0.0, happy with that. So I've clearly put my question mark in the wrong place. Oh, I see, yeah, I didn't even put a question mark. Okay, let's do 1 to 3 as well, because actually it makes no sense to just put a dot. Okay, try again. All 0, yep. All 15.5, yep. All 15 point, invalid. All 15.55, yes. All 25.555, yes. 30.5555, invalid packet. Okay, that's good. 50.999. Can you resolve to all 50.001? Oh, tiny bit of movement there. Anyway, enough torturing the servos. So that's good. The other thing, I mentioned earlier was that we've got the limits now imposed in Python on the receiving end of the socket, but we haven't put the limits inside the FPGA yet. So what we can do is here, if the position count is less than the target, I'm going to say or the position count is less than t min. and that will mean that if we do give it a stupid target, it's never going to go off the scale like it did just now. Or position count is greater than T max. Sorry, what am I doing? If position count is greater than the target, so we're moving forwards. We're moving backwards, sorry. And, yeah, that's what we want, isn't it? We want an and position count is less than greater than T min. Yeah. Yeah. So that'll put a boundary on it down there. And we want an and less than T max. So it can't keep moving past. It might get a little bit past, but it can't get further than that. Is there a better way we can put a limit on this? We could clock in the target to a local register instead of a public shared with the host register. And we could say if it's less than this, then yeah, let's do that. The position target, I'm going to make that a signal of 24 bits. And I'm going to say in here with m.if. So if the self.reg target is less than t min, pos target equals t min. Else if the register of the target value is greater than t max, there we go. That's actually supposed to be an else if, elif. Otherwise, pos target equals the self.reg target. There we go. That will be much better. And now we can get rid of this logic down here. Brilliant. I'm going to rename target to, or TGT to target, because it just doesn't sit quite right. Target, 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 target. Target, 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 target. I think that's all alright, isn't it? No alignments or whatever messed up. Okay. Limit range in FPGA done. Cool. So that is fully functional. We haven't got the ability to control the frequency in the via the protocol or whatever, so I think that's okay. Put that back to 20 and just see how it works nowadays after all the changes we made. That should be a 50 Hz signal, hopefully, when it reloads. Still building. Building. There we go. That's good. So that's 20 milliseconds, 50 Hz. And if we do a top-down view, and I just do a simple all to 0, I think that's alright, isn't it? All to 100. There you go. And if I show you the scope again, and I say all to 1,000, it doesn't do its thing. It doesn't actually accept the packet at all. So, I forgot about that. So we get this error message saying our position is not between 0 and 100, which I think is fine. Yeah. There we go. I think that might be the servo applet near enough done. Some tidy up to do, perhaps at some point. Wonder if we can optimize this in any way. we got any NMyGen applets, do you think? Can you show the scope when you tell the servos to move? Oh, sure, yeah, okay. I can tell you about that. So what we have is, I won't talk about the MyGen, but I will talk about the scope. Let me just zoom in on that quickly and I'll give you a bit better view. Yeah. Okay. This is a 2 millisecond pulse, and what that means to the servo is that it should be at the position all the way one way. So if I now grab up, let me just run Glasgow again. There we go. So that's a 1.5 millisecond pulse. So if I do servo 0 to position 0, this will go down to a 1 millisecond pulse. And if I do servo 0 to position 100, so that's all the way the other way, it will go up to 2 millisecond. And the servo just uses that to tell it where to go, which is kind of cool. So if that makes sense, yeah, it's pretty simple. And then you just send that pulse like 50 times a second, and depending on the length of that pulse, the servo will just match the position basically, yeah. So if I set it to something nice and slow, like 50, then you can see that pulse changing slowly. And if you watch in the bottom, you can also see that servo is just moving slowly as well. Yeah, so the 1 millisecond to 2 millisecond pulse is gives you the position that the servo should go to. The reason you've always got the 1 millisecond is so that you've got something to lock onto. You know, there's an active signal. If you went all the way down to 0, then that wouldn't work out so well, because obviously you'd end up just with a low signal with no sort of transitions on it at all. You can, with a lot of servos, actually go below the 1 millisecond point. I think these ones might do it, so let's just have a play with that quickly. Yeah, it's really simple. It's pretty nice, to be honest. Let's just yeah, fine. Yeah, okay. So if we tweak this, then the resolution. So the number of pulses per second gives you the update rate. So the servo knows. The servo knows that it can what its position should be every time you send it a pulse. The resolution is then how accurate you can be with that pulse. So are you going to send a 1 millisecond pulse and then a 1.1 millisecond, 1.2, 1.3, all the way through to 2 millisecond? That would give you 10 steps or a resolution of 10. If you then sort of increased your resolution, you'd go from 1 millisecond to 1.01 perhaps, and then 1.02, and that would then give you 100 steps, resolution of 100. So what we're going to do is play with this a little bit. I'm going to tweak it so that we can do between, I think, let's go for 250 microseconds through to do that here, 250 microseconds, 250 minus 6, and then let's go all the way up to 2.75. So this is opening up way beyond the typical range, but I think these servos might be able to follow that far. I need to do another change down here to accept. 0 to 100. Yeah, okay, so this will need to go from 0.25 to what have we got? 0.75. Oh no, not that. 2.75 minus 0.25 is 2.5. So the range of 2.5. There we go. The YouTube issue. Yes. So I'm actually quite lucky. I saved the stream as a file on the computer, and I had multiple audio tracks. So I had my talking audio, but I also had then the computer audio with the music in it. So I uploaded it first time, and it said, "Oh no, you're not allowed to do that because you got copyright strikes or whatever against you." So I had a look into the options, and there's seemingly quite a cool option where you can get YouTube to mute out the music which is copyrighted but keep all of the other sounds. But it didn't work for me. I had to submit things multiple times and stuff, and there were loads of songs that it recognized as well. So what I actually did is just uploaded it with no music, just my voice. The other issue I had was because I stream kind of in the evenings, and so when I'm done, I then go off to bed, and I use a command line tool to upload the video to YouTube, so I can just set it running and turn my computer off, leave my little computer running. And it didn't like that for some reason, and it kept flagging it as spam, and I can't remember what it was now, misleading content and stuff. And it's like, yeah, no, it's not misleading. So really annoyingly, I had to upload it with the browser after that, and then it worked. That was frustrating. I might try again with the command line tool and just see what happens, but I'm not sure I'm going to sing. Sorry. Okay, so now I'll put you on the scope again. We've got the ability now to go between about 250 microseconds and 2.75 milliseconds. So if we go for 0 to, let's go for 0 for 25%. Oh, that went the wrong way, I think. Let me just zoom out a bit as well. Okay. 0 to 25 and 0 to 75? Something like that. Okay, we got something wrong in the code. Let's come back to the code. 1 plus target val. Target val is 0.25 times. No, that shouldn't be that. I think it was even 1.0. That's not right, is it? That's better. Okay, let's try that. Okay. So servo 0 goes to 25%. No, it's done the same thing again. 0 to 75%. No, okay. So target float divided by 100 gives us a 0 to 1 value. Oh, right, okay. What we actually need now is a 1. So that's the 1 millisecond, 1e minus 3 plus the target value times 2.5 e minus 3 as an integer. There we go. Okay, what do you reckon? 0 to 25%. That's better. Okay, so I'll show you the scope. Hopefully you can see these servos in the bottom right hand corner. If they're a bit small, do say, and I will make them a bit bigger. If we set that now to 15%, that comes to 1.3 milliseconds. So that's still in range. Let's go for 10%. 1.2, 0 to 5%, 0 to 0. Have I got this wrong again? I have, haven't I? Yeah, sorry. I'm good at maths, me. So 250 microseconds, there we go, because we tweaked the start point. Okay, so watching this go, 25%, 0 to 25%. There we go. So that's actually out of range now. And if we go for 0 to 20%, it's still moving. And if we go 0 to 15%, yep, still moving. 0 to 10, yep. And that's hit the end stop, I can hear it now. So if I go to 11, there we go. So this has gone all the way down to about 525 microseconds as the shortest pulse. And if you can see here, it's pointing that way. If I then go for 0 to 85%, I'm going to turn all the way to there. I'll show you the scope. So that's now a 2.37 millisecond pulse, and that's again way out of range, or the expected range, which is typically 1 to 2 milliseconds. And here we go, sorry. So it's pointing this way now. And if I do to 90%, 0 to 92%, 95%, what do you reckon? Oops, 95, sorry, not 85. Still happy. So 0 to 100, pretty much there, I think, wasn't it? Okay, so it hasn't actually moved past 95%, even though our pulse width changed. Yeah, as you can see here, we're now 2.62 milliseconds, and that's way out of range again. So I think our range was something like 11 to 95-ish. And that's technically out of spec, I think, but because these servos are cheap and various other reasons, that's kind of happy to do it. So yeah, hopefully that kind of fills you in. Actually, I think, let's have a quick look. I had a feeling that servo ppm, there you go. Yeah, so different servos with different constraints on their rotation, but the neutral position is always around 1.5 milliseconds for pulse width. Most RC servos will move to the same position when they receive a 1.5 millisecond pulse every 6 milliseconds. That's much faster than we're doing. As long as the refresh rate, and how many times per second the pulse arrives, is a range of 40 to 200, the rate of the refresh rate is irrelevant. Okay. So yeah, we're aiming for a 50 Hz refresh rate because that's kind of typical. But it looks like we can actually reduce that or increase the rate quite significantly. But I think maybe that, yeah, let's just do that now as a command line argument real quick. Should we do min-max as well? Kind of tempted to do min-max. So we've got min-max as values here. Let's just do the frequency, the period. Oh, how they work on the inside. You basically have a little DC motor, which is wired up to a gearbox or hooked up to a gearbox, and then that increases your torque but reduces your speed, obviously. So the little DC motor can spin quite quickly, and through the gearing you then get quite a slow output, but the torque on it is quite considerable. And then on the top of that output shaft you then have a potentiometer. And basically the difference between the demand position and the current position is then calculated and dealt with so that you then get a directional control over the DC motor. So you either drive the motor one way or the other way. And I think they tend to have kind of PID type loops in there as well so that you don't get too much overshoot and that kind of thing. But it's pretty cool. I don't have one to pull apart, unfortunately, but yeah. Have a look. I'm sure someone will take a big one apart because I've got little ones here, so they're not going to be very interesting on the inside. Anyway, let's put the let's just quickly put the frequency in there. What did they call it on here? I'm going to call it frequency. It's not going to be that, though, is it? Okay, parser add argument. It's finding you. Okay, yeah, neat. Let's call it frequency. Okay, so now we should have that available for us to use. We can pass that into the gateway. I'm going to make that a build argument so that it will rebuild if we change that, because it's not something you should really change much. ppm freak, let's call it. Oops. He's lined up quickly. So args.frequency, and that comes into servo here. ppm freak. Oh, you want to make one? Oh, absolutely, go for it. You get some continuous servos as well, so that they have no end stops and they just go round and round and round. And the PWM, or the width of that pulse that we've been looking at, determines the speed forwards or backwards rather than an absolute position. They're quite cool. It might be easier as well to deal with initially, but then you've got to have a special pot which can go around and round and round as well. And then it's a matter of how do you deal with the dead point where the pot loops, if that makes sense. Oh, okay. I think a lot of them, to be honest, are going to be digital these days. But back in the beginning of Hobby RC, which is where this stuff, I'm not sure about originated, but I'm going to say originated. They would have been analog. So you can change or convert a pulse width into an analog voltage quite easily, I think. So the idea there would be that you have a voltage coming out of the potentiometer and a voltage coming out of your pulse to analog conversion, and you then look at the difference between them and send the motor going one way or the other way based on that. I might be wrong there, but I would imagine that as analog circuitry in the original servos. Okay, T-Psych, here we go. Okie dokie. I'm going to put a range limit on this, I think, as well, so I don't go too far. ppm freak equals. So first of all, we need to do 1 over that. Oops. To turn a 50 hertz into a 20 millisecond. And then we want to do if ppm freak is less than 10 hertz. If it's greater than, what do you reckon, 400 hertz? 400 hertz in English. 2.5 milliseconds. Now we can simplify this. What we can do is a minimum of 1E3 or the maximum of 2.5E3 or that. Yeah. So ppm frequency, and let's also put the it's not actually ppm frequency though, is it? It's the ppm period. ppm period freak. Let's rename that variable quickly, otherwise we'll have problems. Okay, so if we now run this, just by default we should get, oh yeah, was rate not defined, 129. Rate A, put an A in there by mistake. There's no attribute frequency, 132, okay, what was it going to be, freak? No. Did I spell it wrong? Is that the next issue? Frequency. There we go. Okay, by default, that's wrong. We want the max of those and the min of those. Oops. Okay, there we go. So 50 hertz is what we've given by default. Let's do frequency is 25 hertz. Yep, happy. 10 hertz. Happy. And if we do 5 hertz, it should lock it to. Oh no, what do we go for 1 hertz? Oh, okay. Oh. 1 over the frequency gives us the time. We're going to want the minimum. Oh, E minus 3. Apologies again, I think. There you go. Yeah, so 400 is the fastest we can go. Might have had these the right around to begin with. There we go. The code you change the PWM frequency period is a bit of Glasgow side or host Python side. This is actually the host side. The anatomy of an applet. So this is the sort of top level class that describes the applet. You get some build stuff, so what gateware needs to be done and any arguments you need to produce that gateware. Then you get some run stuff, so how do I make that gateware work, and again any arguments you need, which I don't have any in the moment. And then finally you get the interact phase or section, which is if anything you need to do, like prodding the gateware to make it do its stuff or let the user interact with it, again with arguments. And so all of this comes together at runtime. You build it, you set it up and you run it, and then you interact with it. And the actual gateware is then at the top. I can run you through it really quickly if you've just joined and you missed the previous stuff. So yeah, at the moment here I've added the frequency argument to the build step, and then we are taking that frequency and we're making sure that it fits within a range. So it needs to be the max. I keep getting this backwards. Maximum of 1 millisecond or the custom value, and the minimum of 2.5 milliseconds or the custom value. Let's just resolve this quickly and then I'll walk you through it real quick. So a frequency of 1 hertz is out of range, and that's fine that it's out of range, but why is it giving us that? Let's put 50 in. It's still giving us 400. Let's just do an exit here quickly. Apologies, let's just resolve this quickly. Frequency of 50. Yeah. So we've got ppm period equals 1 over okay, you can use that here. Okay, so the ppm period is 2 milliseconds, that's fine. Then we want the ppm period to be the minimum of 2.5 e minus 3, which is 2.5 milliseconds, or ppm period. And it's oh, sorry. What have I done 2.5 in there? That's way out of spec. That's 400. So 400 hertz is 2.5 milliseconds. 50 hertz is 20. Yes, we do want max of that. Okay, Okay, so that's come through there now. And then we want the minimum of 1e minus 3. Oops. And I don't think it's 1e minus 3, so 1 over 400 gives us 2.5 milliseconds, but 1 over 10 gives us, 100 milliseconds. That's the problem. Better. Okay, so now if we give 10 hertz, it's good, and if we give 5 hertz, it locks it to 10. If we give 50, good. If we give 500, it locks it to 400. 400 is that again. Okay. There we go. Apologies, that was a little bit of Atty having problems with maths again. Let's pop that in there. And let's pop that in there. And let's put that just there. Okay. That should all be happy now. Okay. I will show you the scope when this gets up and running. And we should see a period of 2.5 milliseconds. Like that. Let's put the measurement of, we're going to put in the frequency. 400 hertz, yeah. So you can see on the right hand side there, we've got a period of 2.5 milliseconds, which is 400 hertz. We've got a width of 1.5, and the top is the 5-volt signal. So if we change that then for a 10 hertz signal, I'm going to go way off the end of the screen, but the counter I think should still be okay with that. And this is taking a little while because it's rebuilding, because the frequency is a build time argument. It will then actually realize that that's changed, and now it needs to rebuild the gateway. Scope's a bit unhappy because it's triggering and then there's a big delay. But if we zoom out, there you go. Making it 100 milliseconds or 10 hertz. Perfect. Vim is brilliant. If you're not done much Vim, then I highly recommend you get into it. Yeah. So okay, let's have a quick walk through the NMyGen. So I mentioned earlier, this is all about setting it up, configuring it, how to work it, and then how to poke the gateway so that it actually does something. What we have up here is the main subtarget, and this will instantiate one channel per servo that we specify. So on the command line here, we can do pins out 0, 1, 2, 3, and that will actually instantiate 4 servo controllers, and we can control each of these 4 servos independently. So that just does that 4 times. And again, because it's a build option, and because Glasgow will actually reproduce the gateway at runtime, this is something that's just completely dynamic. I don't have to say, here are 4, only enable the ones that are necessary. I can just say, produce the ones that are needed. And then this is 1 channel's worth here. So what we have is the min and the max, the min, the middle, and the max values here. So I'm going to actually put them back to, I think let's go for 500 microseconds and 2.5 microseconds. Let me just confirm what 400 hertz is. 2.5. Okay, so that's quite tight. Let's go for something like 2.25 then, and 750. That way we can always get a pulse out of it, no matter what settings we have. So these are min, middle, and max. And then we got the cycle. So this is the cycle time, the period time, and that is what we're now giving on the command line. So it takes the clock frequency, which is 48 megahertz, and the value that we give on the command line. And then we got the cycle count and the position count. and these then control the output that we're putting onto the servo to give its position, basically. We've got then target value, position value, and the position rate as well, so how quickly that rate can change. We basically do a little bit of min-max boundary control here, so that the pulse that we generate can never be out of range. So if it is out of range, then we what's the word? Can't think of it. We lock it to the minimum or the maximum, depending. And then if it is in range, then we just use the value that we're given from the register. And then here we will run this loop, basically, or not quite a loop because of how it works in HDL stuff, in gates rather than procedural programming. But what we effectively do is run around this, and each time the clock. Let me draw on a piece of paper again. Can I squeeze that in? Rid of me. Okay, so what we have is this period from here to here, say, and then it repeats, does it again. And what you want to do is produce a pulse that starts here, so there's always going to be a rising edge at that point, and then this width is going to be variable depending on where you want to send the servo. That's a variable width. And then you want to do nothing, 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 and start again. And again, that's the variable width there. So this control, what we do is we say this is time 0, this is time 0, so it resets at that point. And we count up. We count up and up and up and up and up. And that up counter is happening here. So we get the cycle count just goes cycle count plus 1. And when you then reach this point, that's the beginning of the pulse that we're going to generate. And because of what this is, it's always high until the pulse starts, and then it's high until the pulse ends, and then it just remains low for the rest of the period. What we can do is just to very simply say, if the cycle counter is less than the position counter, then just output a high value. So that's what's happening here. We have a cycle counter which maybe points at this point here, and it's counting up and up and up and up, and then when it reaches this point, it's no longer true, so the output goes low, and then it waits, just keeps counting up and up and up and up all this duration, and eventually it gets to the next point, which is the T cycle here, which is what we've defined or derived from the period that we gave on the command line. So when it reaches that point, it then resets the counter to 0. So we can start again, which is important. And then it then also does the step change. So if the current position is less than the target, then it will try and push the current position forwards. And it will do that by a maximum of the position change rate, but it will also potentially push it forwards by a smaller amount. So if we're too close, if you have, say if this is our rate here, and we're currently at this point, but we're aiming for a target which is kind of in between, you can't just increment by a whole value or whole jump, because you'll hop over it. And then you'll be too far, and so you'll then hop back, and then you'll be too far, so you'll hop over. So you go backwards and forwards, and you hunt backwards and forwards over it. So what you actually want to do is realize that it's closer than a jump, and move directly to it instead of the full distance that you want to move. Hope that kind of makes sense. Yeah, exactly. So it remembers where the position is, and it will then slowly allow it to push towards that target, the desired position. And that's all done in the gateway here. So if you set it off moving, it will then slowly move to its destination, and then when it reaches there, it will stop. And that comes for two reasons. One reason is that you might want to have the ability, let me give it a quick demo. You might want to have the ability to, let's get rid of that. Say you wanted to move a servo quite slowly between two positions, and you want it to be smooth in that operation. It doesn't, you want it to actually sort of transition rather than jump. Hopefully you can see servo 0, which is this one here. So if we put 0 to 100, there you go. So that's a really nice smooth movement, and 0 to 0, again, really nice smooth movement back. If I was to set this to a really fast rate, I think 10,000 should work. 0 to 100 at a rate of 10,000. It's really quick. But what that does actually is a number of things. So first of all, that draws quite a lot of current from the power supply. Because the destination is so far from where it currently is, the servo will basically dump loads of power into that DC motor to get it to move fast. Again, the other way, it will use a load of power to make it happen as quickly as it possibly can. And that's actually quite an important statistic or parameter of servos. Oops. All right, there you go. Just want to turn me on again. That's quite an important parameter of servos, is its degrees per second, basically. The other thing, so, well, I can't remember what I said now, but yeah, so thing 1 is the current, and thing 2 is the smooth operation. So if you wanted to go from 0 to 100 really, really smoothly, you could either set the FPGA off doing it, like it's doing now, and this is completely under control of the hardware. This is not the computer doing it. And it's now really, really smoothly just changing that value, the width of the pulse really, really slowly. If I show you the scope, you can actually see that. See here, the width of that pulse is just getting a little bit wider every time. And what this means is that you don't have the jitter. So if you're under software control, there's immediately going to be jitter. You might give the update on every single pulse, or you might not, because you might be sort of out busy doing something else. So this gives you the really smooth operation.
Chord progressions, sounds, little ditties, tiny things.
So I hope that makes sense. Yeah.
Just snatch them all up.
So this is really neat. I'm quite chuffed with how this has come out. And if I just bring it slightly back into view again, you can do all to 0%, for example, and they'll all go. And if I set them up quickly, if I do a different speed for each one, do that.
And that's one of the reasons why I can churn stuff out, is because I don't have...
I can now send them all going to 100% position, and they will go at different speeds according to their configuration. So if you just watch that, there you go, look at that. I think that's cool.
And I used to, because I thought it was not original, not creative. But I so quickly found out that I am not...
Yeah, so back to the code. Oops. Probably not a load else to show off here, but it's fairly simple. A nice little pulse generator. It's something that could potentially change into a PWM control, I guess. But for servo operation, there are desirables that you don't have with PWM. So if you're trying to dim an LED, for example, you probably don't want this smooth change from one place to another, or one value to another. You want to just probably jump or... Yeah, anyway. So yeah. Did you order one with on the crowd supply campaign? Very good. Welcome to the club. Speaking of, let's check it out. I know Esden and people have put so much effort into this. Glasgow crowd supply. There we go. 615%, 864 backers. That's awesome. Not sure that Esden's looking forward to dealing with all those orders, but 2 early birds in a case. Very nice. Lucky. Not so bad. No. What was the money at, actually? I just remembered. 150k. That's amazing. Yeah. Anyway. I think that might be the end of today's stream. Hope that's okay. I will be planning to polish this applet up and probably submit it as a PR to the main repo so that we can get it in mainline. Seems to have come along quite nicely, and I'm sure there are going to be things to tweak and make nicer, but yeah, I think that does the job. Very cool. Anyway, 1,000, yeah, I think it was a few days ago someone said, I wonder if we'll get to 1,000. Sure enough, we are pretty close now. But anyway, I think that does me for today. If there's any last minute questions, feel free to just jump in and ask away about what we've done or anything else about Glasgow, feel free. I've got some time to respond. But otherwise, I think I might be coming to a close.
It's easy to churn out a lot of songs if you have a lot of...
One of the other applets I've been working on actually is a frequency counter. I could just show that off quickly. It's not something that I need to work on right now. Just get rid of that. I can't remember what it's called now. Probably ripple counter. Yeah. No. Freak counter, here we go. Yeah, so the idea here is that you can count the frequency of a digital signal. It's not going to work, but if I do just run. Oh, sorry, you're not watching the screen. There you go. You're watching me. Okay, so if I just go and turn the signal generator on, we can get, this is set for a 1.101 kilohertz signal. And if we run it, we get, oh no, it's not plugged in. Of course it's not going to work. Get these all wired up. Down to there. I think I'm going to just plug this into pin 7. Pin I is 7. Oops. Oh, it's got help on there still. This is just a really simple frequency counter. And there you go, 1,000 or 1.101 kilohertz with a plus minus 500 millihertz resolution. That seems to be working quite nicely. So that's hopefully going to appear soonish on the mainline repository. But yeah. Anyway. Tell you what, actually, if we go, this is another neat thing that Glasgow can do. If we go into Glasgow software, Glasgow applet, interface, I think, frequency counter. Where did I put it? There we go. So what you can do is just run a Python file here. So what I'm doing, instead of the applet, which by itself will just run the counter once and then quit, what I'm going to do is run it for a half second each time and print out the stats that it's recorded. So you can see the frequency change over time. And by using the script run mode and giving a frequency counter.py, the file that I've just written, I can run this over and over. I need to do pin I as 7 again because it's plugged into a different pin. There we go. Now, because it's running for only half a second instead of any longer duration, you get a reduced resolution. So here it's only able to see 2 hertz as the sort of the granularity of what it's able to see. So you'll see the value here flipping between 1.1 kilohertz and 1.102 kilohertz. But if I run over here and change the frequency, it should respond accordingly. There you go. And I can turn that all the way up. 10 megahertz is kind of the limit I can do, but there you go. 9.99 megahertz. So that's kind of cool. I'm quite liking this one as well. Anyway, I think there's been no questions, so I'm going to come to a close now. Thank you everybody for joining. It's been quite fun. Servos will probably be, I'll make a PR probably tomorrow, maybe the next day. See what happens from there. And yeah, cool. No problem. Thank you everybody for joining. Maybe see you next time. And until then, stay safe. Yeah. Happy New Year as well, by the way. Oh, that's tonight. It is already the 31st here, so yeah, next time will be 2021. It's kind of crazy. Anyway, I'm going to say goodbye. I'm going to run off to do a bit of sleeping because I'm getting quite tired. So yeah, thank you all for joining and speak to you soon. Bye-bye.